Welcome back. This is Jason Harrington, and today we're going to talk about direction fields. Specifically, we're going to give a precise definition of what a direction field is. Then we're going to talk about autonomous differential equations, and then last we'll finish up with some isoclines. So first, the precise definition of a direction field that we're going to be using, it's going to be a plot of line segments drawn at various points in the xy plane, showing the slope of the solution curve. Now, the idea is that when we're given a differential equation, the neat thing is that we are already given the derivative right off the bat. Can you imagine how easy Calc 1 would be if we were just given the derivatives all the time? Well, in this class, we are. So we're going to go ahead and use that. So we're actually given the derivative, and then we just basically have to put the points inside the derivative to figure out what the slope is. So let's go ahead and do an example. I want to sketch the direction field for the dy over dx equals x squared minus y. So I'm going to let this be my multivariate function. So I'm going to call that f of x comma y. And then I'm going to make a small table. I'll have x, y, and then f of x comma y. And basically I'll just put some points inside to see what happens. If I put in 1, 1, then I'm going to have 1 squared minus 1, which is 0. If I put in 0, 1, then I'm going to have 0 squared minus 1, which will be negative 1. And if I put in 0, 2, then I will have 0 squared minus 2, which is going to be negative 2. And so forth. Basically, if I just put in 0 comma y, that's going to give me negative y. So I can see a neat little pattern to that. If I put in values, let's say 1 comma 0, that's just going to be 1. 2 comma 0, that's going to turn into 2 squared minus 0, which is 4. And let's just put one more point for good measure. If I put in 3, 0, that's going to be 3 squared minus 0, which is 9. Now, the idea is I'm going to plot at each one of these points. This corresponds to a slope. So for example, at 1, 1, the slope is 0. So at the point 1, 1, the slope is 0. And at the point 0, 1, the slope is negative 1. So at this point here, the slope is going to be negative 1. And at the point 0, comma 2, the slope is going to be negative 2. So that's going to be a little bit, it's going to be twice as steep as the previous one. And as you'll notice that there is in fact a slope pattern on the y-axis. At the point 0, 0, the slope is going to be 0. All right, now let's try the next one. If I go to the point 1 comma 0, the slope is 1. So at this point 1 comma 0, the slope is also 1. At the point 2 comma 0, which is this little dot right there, then the slope is going to be 4, which is twice as steep as the other one that's up here at 0 comma 2. And you can see how basically just making a table or picking out some points, you can be able to fill out a direction field. Now here I'm going to go ahead and just give you the directional field that I made on a computer, specifically using Mathematica. So I'm going to be given the direction field of dy over dx equals x squared minus y, which I provided below, and now I want to sketch the solution curve with this initial condition y sub negative 1 is equal to 1. So if you look at the actual graph, you'll see that negative 1 here's the x is equal to negative 1. And then the y values at 1 is over here. This is the y value is 1. So they intersect at x equals -1 and 1 right about here. So let me go ahead and put a little dot here, indicating that's where I'm going to start. So that's -1, 1. And what I want to do is I want to follow the curve. And remember, the curve is going to be tangential to each one of these line segments. So I want to follow this line. I'm going to follow the lines. Remember, it's tangential to each line that we have in here. And that's what it would look like on the right. And on the left of x equals -1, looks like it's just going to go down. And so this will be our solution curve to the ODE with initial conditions y of -1 is equal to 1. And what you can do with the direction field is you can actually start it in the other point and just sort of get an idea for how the curve is going to look. Right? And so a direction field, you should be able to visualize what the solution curves should look like, or at least how they behave. Let's try to integrate e to the -x squared with respect to x. If you were to try to do that, and I encourage you to try, type it into your calculator or software or just see what happens. And what you'll find out is that there is no function whose derivative is equal to e to the -x squared, which is kind of bizarre. There's actually a mathematical proof that shows that there is no what we call elementary function. Now, we're not really going to get into what all that means, but just note that there is no function for this. And if you're in statistics, you'll recognize this as being part of those bell curves and whatnot. However, the slope field is really easy. Remember, we know that the slope field at each point is just this function. And what this means is that even though we don't know what the actual elementary function is or what that antiderivative is, we can actually still figure out what it would look like. So for example, if I start here at this particular point, I can see that the elementary, or that the solution would have this shape. Or if I try another point, for example, let's try what happens at, say, up right here, then this is what the solution would look like at that condition. So yes, even though we cannot integrate that to find out what the answer is, we can still figure out how it's going to behave. And I like this example because it's very simple, and it's going to show you that there are some difference equations that are so complicated that you can't solve. Like this is a very simple one that you really can't solve. But yet, knowing the direction field and knowing some other characteristics, we're able to determine everything about how the solution will behave. Here is another definition: an autonomous equation. A first-order linear differential equation is an autonomous equation if it can be written in the form dy over dx is equal to a function of y only. Now, another way of looking at this is I can write it this way too. Y prime is equal to f of y. And if you look at this, then you'll see that that independent variable didn't even matter. So I could ask the same thing with respect to t or x, and it wouldn't even show up in the problem. Now, I do want to have a word of caution though, and that is that if I wrote dy over dx is equal to x squared minus x, that is not autonomous. And you can tell because if you look at this, you see that that is your independent variable. And you want to make sure that you know the difference between that and dy over dx is equal to, say, y squared minus y. And they're going to behave very differently. This one is autonomous. And again, because in this case, you can see that that is your dependent variable. And everything on the right-hand side is written in terms of the dependent variable. All right, so for this example, I want to investigate the properties of the autonomous differential equation dy over dx is equal to y times 2 minus y. And this is a pretty nifty little example. All right, so first things first, I'm going to let f of y equal to y times 2 minus y. Now the first thing I want to do is I want to construct a sign chart. I want to construct a sign chart for f of y. And you'll see why in a second. So I have f of y, which remember is equal to y times 2 minus y. So now let's go ahead and construct just a little sign chart to see what happens. It's a nice polynomial, so it's only going to change signs a few times. Remember, everything's in terms of y. So if I put in 0 for y, then f of y is going to be 0. And if I put in 2, I also get that the function f of 2 is going to be 0. So if for those 2 points, i.e. those are where f of y is equal to 0. Now, if I were to pick a number, say, smaller than 0, and I were to put that back into the function f, if I put in -1, that's going to make that negative. And if I put a number between 0 or 1, it's going to be positive. And if I were to put a number between, say, or larger than 2, like 3, that's going to make that negative. All right, so the second thing I want to note here real quick before I start working with the sign chart is that the solution y is identically equal to 0, constant, that solves the ODE. That is, in fact, a solution for the ODE. And also, y is, and again, the 3 equal signs, or the 3 right there, means identically equal to, it's just a constant. So it's y is identically 2. That is a constant. So both of those solves the ODE. And you can try it, right? If I were to put 0 inside of here, the right-hand side is just going to be 0 for all y. And the derivative of 0 is 0. Same thing here. If I were to put 2 in the right-hand side, then the right-hand side is always going to be 0, and the derivative of a constant is also 0. Now these have special names. These are typically called the equilibrium solutions, and we'll see why in a minute. So these are called the equilibrium solutions. Which we'll see in a minute visually as to why that's true. And the way that you actually solve these things is simply by taking the f of y and setting it equal to 0. And we'll see why these are actually have the name equilibrium solutions when we start to graph these things. Now the third thing I want to do is I want to take this sign chart that we made. And if you look at this hard enough or squint your eyes, you'll notice this is really just the y-axis laying on its side. So what I'm going to do is I'm going to prop this back up so that it's in the proper form of a y-axis that you're used to. So here I'm going to write this as my y-axis, and I'm going to have my 0 and 2. Now let's go back and look at this curve that we did in number 1. Now don't forget that the function f of y, that's the derivative. Right? That's the derivative. So what I'm saying here is that the derivative is going to be negative, then the derivative is going to be positive, and that the derivative is going to be negative. But what does this actually say about the solution? So I'm going to have y, of course, is the solution. And if the derivative of the solution is negative, then that means it's going to be decreasing. And if the derivative is positive, that means that the solution should be increasing. And if the derivative is negative, then that means the solution should be, again, decreasing. All right. Now, let's go back and look at this, that we have it propped up correctly on the y-axis. So we're saying that everything from negative infinity to 0 is always decreasing. So it's always going down. The slope is going to be negative. And from 0 to 2, the slope is positive. It's always increasing. And from 2 to infinity, we see that it's going to be decreasing. Now this image that I just made, this is called a one-dimensional phase portrait. And it's going to tell us a lot about how the solution is actually going to work. Now here's what you have to understand. For each and every single x, so if I were to draw out the x and y axis here, it doesn't matter which x I pick. If I were to pick x is equal to 1, for example, I know that the y value, y is equal to 2, and the y value here for y is equal to 0, everything is going to happen the same. Everything below this, y is equal to 0, the slopes are decreasing. So it starts off at 0, and then you can see that it just slowly gets more and more negative. And likewise, between 0 and 2, it starts off at 0, but then it's going to get really steep at some point, but it has to be increasing. Remember, it's always increasing. And then it's going to then start to level off again. Now, for those of you that remember your Calc 1, the steepest part, that's going to be your inflection point, where the second derivative is equal to 0. That's just sort of a side note. But you'll notice it starts off at 0, it's going to get kind of steep in the middle, and then go back to 0. And then you'll notice that everything above 2 is just going to be 0, then it's going to move slightly negative, so forth. And what's cool about this is that since this is an autonomous, as soon as you make one sign chart for just say x equals 1, then they are all the same. X equals 2, that is just, you just make a copy of it. And, x equals 3, then you just make a copy of that over and over again. And you place them down there. Now I'm going to show you a picture of all this together, but here's what I want you to know right now before I show you the picture. In this phase portrait, remember I said everything on this phase portrait tells us what the solution is going to behave like. It'll make more sense when I show you the next slide. But remember, everything above 2 is going down, and everything below 0 is going up. So if I were to repeat this over and over again, right, let me just put some dots down. I'm just going to have it's going to look something like this. It's going to start off flat, steep, then flattens back out, then you see that the curve is going to go up and approach 2. And likewise, everything above the 2 is going to go down to 2. We call this asymptotically stable. So we say this is asymptotically stable. The next thing we have is everything. Notice that the 0 here, everything is repelling. See, this stability means it's getting closer, both sides of it are going to something. To be unstable, it has to be repelling. So we call this one asymptotically unstable. Now granted, this may not make sense until I show you the picture, but just remember, all the basic idea for this particular slide is you just had to make the direction field for, say, 1x value, and then all you had to do is just copy it for everything else left and right of it, and you will complete the whole direction field. All right, so let's take a look at this picture. All right, so now let's look at the direction field for our ODE that we had earlier with a particular initial value condition. Now off to the side, I want to put the phase portrait down, because remember I said the phase portrait tells you everything about what's going on. And let's see if we can see that here. We know that 2 was an equilibrium solution, and so was 0. Now what this means is that at exactly y is equal to 2, remember this is our y-axis, at exactly y is equal to 2, we have an equilibrium solution. So we have y is equal to 2 is an equilibrium solution. And the same thing at y is equal to 0, we have another one. We have y is equal to 0 is an equilibrium solution. Now this is why I was putting the 3 dashes for the equals to be exactly equal. Because I'm not saying that at a point, I'm saying y equals 2, the entire constant is a solution, and y is equal to 0 is a solution. So if I go back to my little phase portrait here, or my phase diagram or phase portrait, whatever you want to call that, everything above 2 is decreasing, everything between 0 and 2 is increasing, and everything below 0 is decreasing. Now what you can see from this graph here is if I were to pick any point above 2, so if I were to pick, say, -2, 3, then this will be decreasing towards the equilibrium solution. And that's true for any point that I pick as long as the y value is above 2. So for example, if I were to pick 1, 3 or 1, 2.5, let's do something different, 1, 2.5 over here, then that would be, of course, decreasing to that as well. So any number that I pick above 2, even if I pick something that's maybe off the map even, you can't even see it, I know for a fact it's going to be decreasing and getting closer and closer to the equilibrium solution. Now similarly, anything between 0 and 2, if I were to pick -1, 1 right here, I would see that that would be increasing to the equilibrium solution. Or if I were to pick, say, 1, 1, which would be right here, it would be increasing towards the equilibrium solution to the right. Now, since all the solutions are getting closer and closer to the equilibrium solution, that's why we call this one stable. And at 0, we see that everything is going away from the equilibrium solution, y is equal to 0. In this case, if I were to pick any value, like let's just try 0, -1, for example, that's just going to go right off. Right? If I were to pick, let's say, -2, something close to 0, we can see that that's going to also go away from it. Let's try something like 0. Let's get really close to it. If I get really, really close to y is equal to 0, but still not 0, like say 0.1, we see that it's going to, again, go away from it. And hopefully you can see that this entire direction field that I have over here can just quickly be summed up by this little phase portrait that I had here on the left. So for example, if I pick anything between 0 and 2, it's going to asymptotically approach the stable equilibrium, the stable equilibrium solution, y is equal to 2. It's never going to equal y equals 2, but it's going to asymptotically approach it. And if I pick anything bigger than 2, again, it's going to be decreasing asymptotically to 2. And if I pick anything less than 0, it's going to asymptotically go away. It's going to asymptotically diverge from 0. So this little phase portrait that I drew over here on the left-hand side is really all you need. Instead of having to do all this other stuff that I had over here, you can just simply look at this and say, yeah, now I know everything that's going on. And that's why those phase portraits are so important. So when it comes to our phase diagrams, or our phase portrait, we really only have 3 cases. Case 1, if we have an equilibrium solution that everything is going towards, we call that stable. 2, if everything is going away from that point, we call that unstable. And third, if it is neither, then it'll either be going, let's say it's going away and it's going towards, so just kind of maybe passing through it, or maybe it does that on the way down. So here's why not. And suppose it's going towards above and then going away on the bottom of it. We call that semi-stable. All right, so our next definition is an isocline. An isocline for the difference equation dy over dx is equal to f of x comma y is the set of points in the xy plane where all the solutions have the same slope. In other words, if I say something has the same slope, that's just saying when is this constant. Now this is a neat note for those of you that may have had Calc 3 or thinking about it. An isocline basically says when is the derivative constant. So in other words, when is the dy over dx constant. But in Calc 3, you ask, well, when is a multivariate function constant? And in this class, believe it or not, they're one and the same. So an isocline for dy over dx is exactly the same as just saying, what's the level curve for f of x comma y? For this example, I'm going to let the ODE just simply be x squared plus y squared. And I want to find the isoclines for which the slope is just 1. So now if I look at this, I'm just saying this is now my function f of x comma y. And I want to know when is the function f of x comma y equal to 1 over here. And that's going to happen, i.e. precisely when I have x squared plus y squared is equal to 1. So if I were to look at this in the directional field, I have x and I have 1. I'm going to have this circle of radius 1 at the origin. That's a circle, in case I can't draw one very well. So what does this mean exactly? Well, if I were to have some, and I'll just put here in quotation marks, some solution curve that I want to have, the solution curve that I start off with, right, may look something like that. Now, everywhere our solution curve intercepts or touches the isocline, the slope should be 1. Now let's go back and look at this. Remember, here is my ODE, and I'm saying that I want to find out when the solution is going to have the derivative 1. I want to find all possible cases for which that's possible. So if I say the derivative is equal to 1, here I get a circle. Therefore, I know if ever there is a solution out there somewhere, as soon as it touches this circle, I know that that derivative should be 1. And the only place where the derivative of the solution should be 1 is on this circle. So let's try this again. For this example, I have dy over dx is equal to x squared minus y. Now in this case, again, just like before, I'm going to say f of x comma y is going to be the right-hand side. But now instead of just equaling 1, I'm just going to say let that be a constant. So I want to figure out what happens when you have f of x comma y is equal to a constant. This says that I have x squared minus y is equal to c. And again, I'll just put this up here. That's just a constant. If I were to solve for y, then I would have negative y is equal to negative x squared plus c. So then y is just equal to x squared minus c. So if I were to graph this out, some isoclines here, here I have x and y. If I were to say c is equal to 0, I would have a nice parabola. Y is equal to x squared. Now I know that if any solution were to hit this red curve, then that means that that derivative has to be 0. All right. And if I were to go down a little bit, let's try this one. How about c is equal to 1? Then I will have x squared minus 1. Whoops. I'm not very good at drawing. So in that case, every time the solution curve hits that blue curve, then that means that derivative is going to be 1. And so forth and so on. And you can even draw what these things will look like. So when c is 0, if the solution curve ever hits this red curve, that means you're going to have the slope is 0. If I have c is equal to 1, then I have this blue curve, and everywhere on that blue curve, the slope is going to be 1. Now this is actually called the method of isoclines, where it's actually easier to figure out what the isoclines are and then just graph them all and fill out the direction curve this way. But let's take a look to see what this actually looks like. So I'm going to go back to this example, dy over dx is equal to x squared minus y, and see what the direction field looks like. All right, so let's put all this stuff together. Here I have the direction field with the isocline. Well, first, let's just look at x squared. So again, here I'm going to have f of x comma y is equal to x squared minus y. If I look at, in this case, f of x comma y is equal to 0, that means that the slope is 0 for every single solution that touches that. So the direction field is 0. If I put a little dot here, so again, the direction field is 0 at 0. And then if I follow along, another point that it intersects in the middle is this guy here. You see that at every single point, the direction field is going to be 0. Now obviously I sort of spaced out the field a little bit more from the previous time we looked at this specific example, just to give us some more room, but you can go back and look at that. Now for this guy, let's do the blue one, the next blue one here. Here I'm going to have f of x comma y is equal to negative 0.5. So for that blue, again, I look at the dot here, I see that it's decreasing by a half. And in fact, it should be the same, I don't know if that quite goes through that, but that should be, whoops, negative slope on the blue. And finally, this green one that we have, I'll also just do this one in blue, to make that one easier to see. This is going to be f of x comma y is equal to 0.5. That means the slope is going to be a half every time the green line passes through it. Now don't forget, this is what a solution looks like. So if I were to graph a solution for this, what you'll see is if I were to graph something like here, going down, and then back up. So again, that's what our solution is going to look like. You can see that here, your solution has a max. Why does it have a max at that particular point? Because remember, when it hits the orange curve, the derivative is 0. Just like on this side over here, when the solution hits this curve, the derivative is also 0. So there's your minimum, right? And when it hits the green line, remember the slope should be 1. And I didn't quite go down, it didn't quite go down enough for that one. I was trying to match it out. But you can see that the slopes on the solution curve should match with what's happening in the isocline. All right, so that's pretty much it for this particular section. Now don't forget, if you really want to make sense of all this, you have to kind of graph some of these things by hand to kind of get your hands dirty, as it were, to sort of see how all this stuff goes together.